Did you know that you've just traveled an astonishing 6,300 kilometers in the last 10 seconds? Surprisingly, you're not out of breath despite this rapid sprint. However, this is not because of your own speed, but rather the incredible movement of the local group, which includes the Milky Way and Earth. Our galaxy is hurtling through space at an incredible velocity of 630 kilometers per second. But how did our parent supercluster of galaxies end up on such a breakneck course? And where are we headed? The first time astronomers captured evidence of this immense speed was in the 1970s. Using cosmic microwave background radiation, they managed to determine the velocity of our galactic home. This background radiation, which originated roughly 380,000 years after the birth of the cosmos and still fills the entire universe today, is one of the most compelling pieces of evidence for the Big Bang theory. However, the conclusions drawn from it regarding our movement left several fundamental questions unanswered. While measuring the speed of the Milky Way was an important astronomical milestone, it also raised concerns. Why was our galaxy moving so fast? A significant portion of this velocity could be attributed to the expansion of the universe, a phenomenon described by the Hubble flow, which explains how galaxies drift apart over time. Additionally, gravitational interactions with our closest galactic neighbors, such as Andromeda, contributed to our overall movement. However, a critical piece of the puzzle was still missing. It seemed as though our entire galaxy was being pulled in a direction that we couldn't fully explain. In fact, it appeared that an enormous unseen structure was exerting a powerful gravitational force on not just the Milky Way, but also every galaxy in our cosmic neighborhood. This mysterious force formed what astronomers have called a galaxy stream, stretching over 800 million light-years. Given its profound influence, scientists named the source of this pull the Great Attractor. The next step was to uncover its true identity. But what force could be so immense that it could drag 100,000 galaxies over such vast distances? The answer lay in gravity. But for the Great Attractor to exert such a strong pull, it had to be unimaginably massive. Understanding its nature proved challenging. Initially, astronomers attempted to observe it using telescopes, only to realize that the Great Attractor was located in an obscured region of the sky. The Milky Way's dense spiral structure, with approximately 100 billion stars concentrated along a plane 1,000 light-years thick, blocked their view. This region, known as the zone of avoidance, made it difficult to directly observe the Great Attractor using optical telescopes. Despite this challenge, scientists were able to study its gravitational effects on surrounding galaxies, allowing them to estimate its approximate position and mass. They determined that it lies between 150 to 250 million light-years away in the constellation Norma and weighs an estimated 10 quadrillion solar masses. However, at the time, no known structure in the universe had such an enormous mass, keeping the Great Attractor shrouded in mystery. Thanks to advancements in radio and infrared telescopes, astronomers were eventually able to peer through the zone of avoidance and glimpse the structures beyond it. What they found was astonishing: an enormous collection of galaxies. The Great Attractor turned out to be a colossal supercluster, a vast assembly of galaxy clusters, ranking among the largest known structures in the cosmos. But this discovery only led to more profound questions. In 2016, researchers using the Australian Parkes Radio Telescope made a breakthrough by detecting a specific spectral line from glowing hydrogen beyond the Milky Way. They identified 883 galaxies in the zone of avoidance, 30% of which had been previously unknown. In addition to individual galaxies, they discovered 3 previously known galaxy clusters and 2 new ones. Given that an average galaxy contains about 100 billion stars, this revelation provided a better understanding of the immense mass involved. However, a surprising twist emerged. While the Milky Way is indeed being pulled toward the Great Attractor at over 200 million kilometers per hour, scientists also found that we are simultaneously being pushed away by another force. This unexpected discovery upended prior assumptions about galactic movement. For a long time, the Great Attractor was believed to be the sole cause of our movement, but astronomers soon identified an even larger structure, the Shapley supercluster, located 700 million light-years away in the constellation Centaurus, the Shapley supercluster is the most massive known concentration of galaxies. Its powerful gravitational forces are so immense that the galaxies within it do not drift apart, despite the universe's expansion. Yet, even with the Shapley supercluster factored in, the Milky Way's movement remained only partially explained. Further, studies led by Yehuda Hoffman of the Hebrew University of Jerusalem revealed another force at play. The research indicated that, in addition to being pulled toward the Great Attractor and Shapley supercluster, the Milky Way is also being pushed away from a vast, low-density region known as the dipole repeller. This void lacks the same gravitational pull as other regions of space, effectively repelling our galaxy and its neighbors. The push from this empty region is almost as significant as the pull from the Great Attractor. This discovery marked the first time that astronomers had identified such a repelling force in space, but the mysteries of the cosmos did not end there. Recently, new research suggested that our Milky Way might not even belong to the Laniakea supercluster, as previously believed. Instead, it may be directly part of the much larger Shapley supercluster. This new mapping of gravitational forces in the local universe has challenged our understanding of cosmic structures. As for the dipole repeller, its very existence is puzzling. The standard model of cosmology does not account for such massive voids, as matter is expected to be evenly distributed throughout space. Yet these voids are there, and some researchers believe that our Milky Way resides within a low-matter bubble. If true, this could help explain the so-called Hubble tension, the discrepancy between the expected and observed rates of cosmic expansion. The higher density of matter outside the bubble could be accelerating galaxies away from us faster than expected. So what will happen when we finally reach the Great Attractor? Surprisingly, nothing at all. Despite our immense speed of over 2 million kilometers per hour, we will never actually arrive at it. The accelerated expansion of the universe ensures that the distance between us and the Great Attractor will continue to grow over time. Instead, we will remain gravitationally bound to our local group, while the rest of the cosmos drifts ever further into the darkness of space. And speaking of not losing sight, if you want to keep up with more cosmic discoveries, simply hit the subscribe button, give us a thumbs up, and join our community. That way you'll never miss out on the latest cosmic revelations. See you soon.